everyone, thank you so much for clicking onto the video. Here are today's learning objectives. The first is to know that amines are nucleophiles, and then to look at the nucleophilic substitution reactions of ammonia and amines with haloalkanes, and this is to form primary, secondary, tertiary amines and quaternary ammonium salts. We're then going to look at the use of these quaternary ammonium salts as cationic surfactants. And then we're going to look at the nucleophilic addition-elimination reactions of ammonia and primary amines with acyl, chlorides, and acid anhydrides. So by the end, we should be able to outline the mechanisms of these nucleophilic substitution reactions and the nucleophilic addition-elimination reactions of ammonia and primary amines with acyl chlorides. So now we're going to look at the formation of primary aliphatic amines. So again, aliphatic just means non-aromatic, so amines that don't have a benzene ring. So when ammonia reacts with a haloalkane, it acts as a nucleophile. And this is due to the lone pair of electrons on the nitrogen, and so we have nucleophilic substitution occurring. And we can form primary aliphatic amines from this reaction. Now, we've actually already seen this reaction before in the haloalkanes chapter when we looked at nucleophilic substitution of haloalkanes. So I'm just going to revisit it very quickly. So the example I'm going to use is the reaction between ammonia and chloroethane. So the reagent we're using is ammonia, and the nucleophile is also ammonia. So we're going to start off with chloroethane. So that's going to be CH3 and then CH2Cl. And again, remember that we have partial charges because chlorine is a lot more electronegative than carbon. So chlorine gets a partially negative charge, whereas the carbon will get a partially positive charge. And now we have the nucleophile, which is attacking. So we have ammonia, and that's NH3. And we also have the lone pair of electrons on the nitrogen. And it's because of these two electrons that ammonia can act as a nucleophile, because it's attracted to the partially positive carbon, and so it attacks that carbon. And then because we have incoming electrons, the electrons from this covalent bond feel a repulsion and move towards the chlorine, and this is how we get rid of the chlorine. So what we form is CH3, CH2, and then NH3. So we've substituted the chlorine for this ammonia. And we also form Cl- because that's what we've taken out, because the electrons have moved towards this chlorine to make it negatively charged. And now something really important to remember is that because the nitrogen has donated electrons to the carbon to form a covalent bond, it is now positively charged. A really important thing to remember about these nucleophilic substitutions with ammonia is that we actually have another ammonia nucleophile which attacks. And so a second ammonia is then attracted to the positive nitrogen. And so here we have the second ammonia, again with the two electrons ready to form a covalent bond. And what it does is that it attacks this hydrogen, which is attached to the positive nitrogen. And then what happens is that these electrons from this covalent bond then move towards the positive nitrogen. And so now we can form the primary aliphatic amine. So what we get is CH3 and then CH2, and then we have NH2. And then the ammonia that's just come in, so this second nucleophile, has bonded with the hydrogen which has left the intermediate that we had. That's become an NH4+. And so this NH4+ then reacts with Cl- to form NH4Cl. So this has come from the NH4+ reacting with the Cl-. And then what we need to know is that this amine, which is formed, this primary amine, also has two electrons on the nitrogen, which are available to form a covalent bond with something. And so we have one lone pair of electrons on the nitrogen. And this is ethylamine. we call it ethylamine because the amine takes priority, and then we have a CH3CH2 group which is attached. So this is the substituent group, and it's eth because we have 2 carbons. Now we're going to talk about further substitution. So we've just seen that ammonia acts as a nucleophile in the reaction with haloalkanes to form a primary aliphatic amine. However, we can also get further substitutions. And so first what happens is that we can form secondary amines from a further substitution. So because of the lone pair of electrons on the nitrogen, the primary amine produced from the reaction of ammonia with haloalkanes can also act as a nucleophile. And so it attacks an electron-deficient carbon atom in another haloalkane. So we're going to look back at our example that we used for ammonia. So we reacted ammonia and chloroethane together to form ethylamine. And so now we're going to look at the reaction between ethylamine and chloroethane. So this is a further substitution. So what we have is that we have another chloroethane, so CH3, and then CH2Cl. And again we have the partial charges on carbon and chlorine. And now the nucleophile, instead of it being ammonia, it's now the ethylamine that we produced in the reaction with ammonia. So we have a nitrogen with a hydrogen, and then an ethyl group, so CH2CH3, and then a hydrogen. And remember that we've got this lone pair of electrons on the nitrogen, and this is what allows it to act as a nucleophile like ammonia is. And so these electrons are attracted to this partially positive carbon, and so move towards it. And then electrons from this covalent bond then move towards the chlorine. So again, we form this intermediate where we have CH3, and then CH2, and then we've substituted the chlorine out for this ethylamine. So we have a nitrogen with 2 hydrogens, and then the ethyl group. And of course we have this Cl- ion again because electrons have moved towards the chlorine and removed it, and so it's become a negative ion. And we also need to remember that this nitrogen is now positively charged because we've given away electrons to form this covalent bond with carbon. And then what happens is that we have another nucleophile come in, just like how we had with the ammonia reaction. But this time the nucleophile is ammonia. So these further substitutions happen when we have a mixture. So we've reacted the ammonia with the haloalkane, and then we've produced a primary amine. But then we've got some ammonia left, and so that's how we can use it as a nucleophile here. So we have 2 electrons on the nitrogen, and so what happens is that these 2 electrons attack the hydrogen which is attached onto the positive nitrogen, and then electrons from this covalent bond then move towards this positive nitrogen. So now we form a secondary amine. So what we get is CH3, and then CH2, and then we've got the nitrogen with the hydrogen and the CH2CH3 group. And again, we've got an NH4 plus ion and a chloride ion, and so they react together to form NH4Cl. So what we formed here is diethylamine. And that's because we've got 2 ethyl groups on the nitrogen, and so we use the prefix di because we have 2 of them. And then we need to remember that this nitrogen also has a lone pair of electrons on it. So this is our secondary amine. And then what happens is that we get further substitutions where we can form tertiary amines. So the secondary amine, which is formed from the previous reaction, also has a lone pair of electrons on the nitrogen, and so that means they can also act as a nucleophile. And this is the key point, is that every time we produce something, the nitrogen still has that lone pair of electrons, and so we can get further nucleophilic substitutions. So again, we have chloroethane. So we have CH3, CH2, and then Cl. And remember, we always have to have the partial charges in. So the partial positive and the partial negative due to the electronegativity difference between carbon and chlorine. And then this time the nucleophile is this diethylamine. So we have a nitrogen with two of these ethyl groups. And then one hydrogen. And the key thing is that we have this electron pair, this lone pair here. And so it's attracted to the carbon and so moves towards it. And then these two electrons from this bond move towards the chlorine due to some repulsion. So what we form is CH3, CH2, and now we've substituted out the chlorine for this diethylamine. So we have a nitrogen with an ethyl group, and then another ethyl group, and also a hydrogen. And again, we form this Cl-. So another thing that we need to remember is the positive charge on the nitrogen, because we've donated the electrons to the carbon to form that covalent bond with it. And again, we have an ammonia nucleophile attacking. So we have NH3. And again, these two electrons target the hydrogen, which is attached to the positive nitrogen, so this one. And then these two electrons move towards this positive nitrogen because they're attracted to that positive charge. And so now we form the tertiary amine. What we get is CH3, and then CH2, and then we have nitrogen with two ethyl groups on it. And again, the NH4 plus formed from this bit here, from the hydrogen, the nitrogen donating the electrons to the hydrogen to form a bond with it. That NH4 plus reacts with the Cl- to form NH4Cl. So this is triethylamine, because now we have three ethyl groups on it, on the nitrogen. So this is our tertiary amine. And then what happens is we get one last substitution, and we form what we call quaternary ammonium salts. So we know that ammonia can only bond 3 times, and then it has a lone pair here. And what it can do is donate this lone pair to something else, and this will form a salt because it will have a charge, it'll be positive. And so what we have is that, again, we have chloroethane. So I'm going to write it CH3 and then chlorine on the end. Again, remembering the partial charges, so we've got partially positive and a partially negative. And then this time the nucleophile is this triethylamine. So we've got nitrogen with 3 ethyl groups on it. Because it's a tertiary amine. And then the lone pair of electrons. And again, they target this electron deficient carbon. And then these electrons from this covalent bond feel some repulsion and move towards the chlorine. And then we form CH3, and then CH2, and then N, and now we have 3 of these ethyl groups on it. And then also the chloride. And now we need to remember again that this nitrogen is positively charged, because it's lost some electrons. And so now we don't get another ammonia attacking as a nucleophile because there's no more hydrogens left on this nitrogen to be substituted out. And so what happens is that these two ions produced then react together to form this quaternary ammonium salt. So this bit here is our quaternary ammonium salt, and how we write it is CH2, CH3, 4, and then the nitrogen, which is a plus, and then Cl, which is a minus. So this is our quaternary ammonium salt. And in this case, what we would call this salt would be triethyl ammonium. So this is what we get from the positive bit, and then chloride. So really important things to remember are that these are all nucleophilic substitution reactions. And that's because the attacking group is always a nucleophile, which has a lone pair of electrons available to donate to something else to form a covalent bond. And we're substituting the chlorine for the nucleophiles, and so it's a substitution reaction. And another thing we need to remember is that the reason why all of these further substitutions happen is because the products that we form always have an electron pair, a lone pair of electrons on the nitrogen, which means that the product can act as a nucleophile. So first our nucleophile is ammonia, and then the primary amine which we have formed also has that lone pair of electrons on the nitrogen, so that can also act as a nucleophile. And that's the same with then a secondary amine, and then finally a tertiary amine. And so we can go all the way to forming quaternary ammonium salts. Now we're going to look at the different conditions for this reaction of ammonia with haloalkanes that we can have. So we know that when we react ammonia with a haloalkane, we get a mixture of primary, secondary, and tertiary amines, and also a quaternary ammonium salt. And because of this, it isn't a good way of preparing primary amines. And so the general rules are that if we want a high yield of primary amine, we need to use an excess of ammonia. Or alternatively, we could have a limited amount of haloalkanes. And this is because this prevents further substitution. Because if we don't have very much haloalkane, or if we have a lot of ammonia, and that's all, ammonia is the only nucleophile that will be reacting with the haloalkane, and so only a very high yield of primary amine will be formed and not as much further substitution. However, if we want to obtain a mixture of amines and the quaternary ammonium salt, we need to use an excess of the haloalkane or a limited amount of ammonia. So this kind of question comes up quite a lot in exams. So just make sure that you understand why, if we want a high yield of primary amine, we need an excess of ammonia, and why, if we want to obtain a mixture of amines, that we have an excess of the haloalkane. So the reason why we need to have an excess of haloalkane to obtain a mixture is because we want loads of further substitutions to happen. And that can only happen if we've got lots and lots of haloalkane react with the different nucleophiles that we produce. Now we're going to talk about the uses of quaternary ammonium salts. So soap and detergent molecules are what we call surfactants. And they consist of an ionic head which dissolves in water. That's because it's ionic, so it can form hydrogen bonds with the water. And also a long alkyl chain, which dissolves grease. And it doesn't dissolve in water because we only have carbon and hydrogen bonds, which aren't polar, so we can't form hydrogen bonds. And the word for dissolving in water is hydrophilic, and the word for dissolving in grease is hydrophobic. So micelles are formed as the soap or detergent molecules surround the dirt and grease molecules, with the hydrophobic tails in the center dissolving the grease, and the hydrophilic heads around the outside dissolving the water. Quaternary ammonium salts with some long-chained alkyl groups are used as what we call cationic surfactants, and these are often used in fabric softeners. So an example of a soap would be if we had a very long-chained alkyl group, and then at the end we had carbon with a double bond O, and then an oxygen, so this is negatively charged, and then we had a sodium plus ion. So what happens is that this long alkyl chain here dissolves the grease. This is because it's made up of carbon and hydrogen bonds, so none of the bonds are polar, so we can't hydrogen bond with the water, and therefore it won't dissolve in water. Whereas this bit here, because it's ionic, therefore we can form hydrogen bonds, and so this dissolves in water. And so the purple bit is what we call the ionic head. And then we have the long chain, which we call a tail sometimes. Now we're going to look at acylation reactions of primary amines. So we've actually already seen this reaction before in the acylation chapter, but I'm just going to quickly revisit it. So when we react primary amines with acyl chlorides or acid anhydrides, we form secondary amides, or N-substituted amides. And this is a nucleophilic addition-elimination reaction because the attacking group is the primary amine, because we have the lone pair of electrons on the nitrogen, which can be donated to the electron deficient carbon to form a covalent bond. And it's an addition elimination reaction because we're adding the nucleophile, but then eliminating something off of the either the acyl chloride or the acid anhydride. So the primary amine acts as the nucleophile. And that's because of this lone pair of electrons on the nitrogen. So for example, if we had ethylamine, so CH3, CH2 and NH2, we have a lone pair here on the nitrogen, so it can act as a nucleophile. So in the example we're going to use ethylamine, and firstly we're going to react it with ethanol chloride. So ethanol chloride is the acyl chloride. And what we get is, first of all, let's draw out the ethanol chloride. So we have CH3, C double bond O, and then Cl. And we're reacting it with ethylamine, so CH3, CH2, NH2. And then what we form is CH3, C double bond O, and then we have NH, CH2, CH3, and then we also form HCl because we've lost one of the hydrogens off of this ethylamine, and it's bonded with the chlorine that's been lost from the ethanol chloride. And so what we formed is N-ethyl ethanamide. And we've called it that because, first of all, we need the N because we need to indicate where this ethyl group is. And we've got an ethyl because this group here is an ethyl. And we also have eth for the prefix of the amide because we have two carbons here and here. And now the reaction with ethanoic anhydride is very similar, but we need to remember that it's an exception. So we have the ethanoic anhydride, which is CH3, C double bond O, O, and then another carbon, double bond O, and CH3. And this reacts with, again, we're using ethylamine. And this will go on to form CH3, C double bond O, N, H, and then CH2, CH3. So we get the same product. And then now what we need to remember is that the carboxylic acid which is formed, which would be this CH3, CH2, C double bond O, OH, this actually reacts with another amine, so another primary amine. So what we get here is plus another one of this ethylamine, CH3, CH2, COO minus, and then NH3 plus, CH2 and CH3. So we get this salt. So then overall what we have is we have the ethanoic anhydride, which is CH3, C double bond O, and then oxygen, another carbon double bond O, and then CH3. And then we add it with 2 moles of this ethylamine, so CH3, CH2, and NH2. And this will form the secondary amide that we want, so CH3, C double bond O, NH, and then an ethyl group. And this time we'll form this salt. So plus CH3, CH2, COO minus, and then NH3, CH2, CH3. So this N-substituted amide that we formed again is this N-ethyl ethanamide. So how we've got these equations, these acylation reactions, is that first of all what happens is that basically we separate off this section here. And this section then reacts with this amine, which has lost 1 hydrogen. And so this is how we get this bit here. This is how we get the secondary amide. Just imagine the amine being flipped round. So if we put a mirror line here and we flip it round, and then bond it with this partially positive carbon, and this is how we get the secondary amide. And then we have the rest of this molecule here, which reacts with the H plus to form what we had as the carboxylic acid here, where we had the ethanoic acid. And this is the same for the acyl chlorides as well. So what we've done is we've got rid of the chlorine and flipped over this amine, and then got rid of one of the hydrogens and bonded it to the partially positive carbon. And then the chlorine and the hydrogen from the amine have then reacted together to form the HCl. So now we're going to look at the acylation reactions of ammonia. So when we react ammonia with acyl chlorides or acid anhydrides, we form primary amides. And again, this is a nucleophilic addition-elimination reaction because this is also an acylation reaction. And this time, ammonia acts as a nucleophile instead of the primary amine that we just saw. So first of all, we're going to look at the reaction with ethanoic anhydride, which is an acid anhydride. So we have CH3, C double bond O, another oxygen, and then carbon double bond O, and then CH3. And this reacts with ammonia. So you have NH3, and this will form CH3, C double bond O, N, and then 2 hydrogens. And what we also form is ethanoic acid. So we have CH3, C double bond O, and OH. So what we've formed is ethanamide. And we call it that because it's an amide and we've got 2 carbons, so we use the prefix eth. And so how we've got this is that we've split up this acid anhydride. And so this first bit here reacts with the ammonia and this nitrogen with these 2 electrons then form a covalent bond with this partially positive carbon. And so this is how we get the ethanamide. And then this second bit of the acid anhydride then reacts with the hydrogen, which has been removed off this ammonia when it's reacted with the first bit of this acid anhydride to form ethanoic acid. And now looking at the reaction with ethanol chloride, we have something really similar. So we have ethanol chloride, which is CH3, C double bond O, and then Cl. And again, we're adding this ammonia. And this time we form the same thing, so also ethanamide. But this time we form HCl. And then what we need to remember is that this HCl then reacts with more ammonia, so another mole of ammonia, to form NH4Cl. So what we get is plus NH3, and so what this forms is NH4Cl. So overall what we have is, we have CH3 C double bond O Cl plus 2 moles of NH3 to form CH3 C double bond O NH2 and NH4Cl. And this is our ethanamide. So again, how we've got the amide is that we've broken off this chlorine here, and this partially positive carbon has reacted with the lone pair of electrons on the nitrogen, and then one of the hydrogens off the ammonia has been removed, and this hydrogen then reacts with the chlorine removed from the ethanol chloride to form hydrochloric acid, and this hydrochloric acid then reacts with another mole of ammonia to form NH4Cl. We also need to know the acylation mechanisms with the acyl chlorides. So first we're going to look at reacting ammonia with ethanol chloride. So what we start off with is the ethanol chloride, which has the formula CH3 and then C double bond O and Cl. And we have partial charges because there's an electronegativity difference between the carbon and the chlorine, because chlorine is much more electronegative. So that gets a partially negative charge, whereas the carbon gets a partially positive charge, and we have a polar bond between them. And then what we have is the nucleophile, and the nucleophile which is acting is the ammonia. So we have NH3 with the lone pair of electrons ready to donate. And then what happens is that these two electrons are very attracted to this partially positive charge of the carbon, and they move towards it. And then what happens is that electrons from this double bond then move to the oxygen because they feel a repulsion. And so what we form is an intermediate where we have CH3, so this bit hasn't changed, and then C, and now we have only a single bond to the oxygen, and it's got a lone pair of electrons now because they've just had electrons moving towards the oxygen. So now it's negatively charged because of these extra electrons. And we also have a single bond to the chlorine, and now this carbon is also bonded to this ammonia. So we have NH3 on the end here. And because the nitrogen has given away its lone pair of electrons, that means that it's now become positively charged. And so what happens next is that we have these two electrons here moving towards this covalent bond. And then what that does is make these electrons from this covalent bond move towards the chlorine, and this is how we get rid of the chlorine. And whilst that's happening, we also have electrons from this covalent bond moving towards this positive nitrogen. And now we form amide. So we have CH3, C double bond O, and then NH2. We get the double bond because of this bit here where we're moving these two electrons to this bond. And then we've got rid of the chlorine here, and we've got rid of the hydrogen here. And the hydrogen, which has been removed, then reacts with the chlorine, which has been removed, and so we get HCl. But now we need to remember that this HCl then reacts with more ammonia to form NH4Cl. And so overall what we have is that CH3 C double bond O Cl, so ethanol chloride, added with ammonia, goes to form this amide, CH3C double bond O, and then NH2, and also NH4Cl. So the amide that we formed is ethanamide because we have two carbons. And now looking at the reaction of ethylamine with ethanol chloride. So this time we're looking at the reaction of the primary amine instead of with ammonia. So again, we have the ethanol chlorides, so CH3, C double bond O, Cl, and again we have the partial charges. So we have partially positive charge on the carbon and a partially negative charge on the chlorine. And then again we have the nucleophile, but this time it's ethylamine. So we have a nitrogen which is attached to a hydrogen, an ethyl group, and another hydrogen. And again we have a lone pair of electrons. And these electrons are attracted to this partially positive charge of the carbon, so move towards it and attacks the carbon. And then electrons from this double bond then move to the oxygen. So again, we form an intermediate. So we have CH3, C, and then the oxygen, which now has the lone pair of electrons on it and is now negatively charged. And then we have a single bond to the chlorine, and now we have a bond to this ethylamine. So we have a nitrogen with a hydrogen and another hydrogen and an ethyl group. And now we need to remember again that this nitrogen is positively charged because we've given away some electrons. And now what happens is that these electrons move towards this bond, and then this causes these electrons from this bond to move to the chlorine, and also these electrons from this bond then move to the positive nitrogen. So then we form our N-substituted amide or secondary amide. So we get CH3, C, and then double bond O. We remove the chlorine, and then we've got a nitrogen, a hydrogen, and an ethyl because we've removed the other hydrogen from the nitrogen. And we also form hydrochloric acid because the hydrogen we've removed reacts with the chlorine that we've also removed. And so this forms N-ethyl ethanamide because we have two carbons here, so we use the prefix eth for the amide, and then we have to say N because we need to know where the ethyl group is placed, and we have an ethyl because this group here is an ethyl. Actually, looking back at the first reaction, we should have two ammonias and not just one. And then the overall reaction, the overall equation for this reaction is this ethanol chloride added with ethylamine, so CH3, CH2, NH2, goes to form N-ethyl ethanamide. So we have CH3, C double bond O, and then NH, CH2, CH3, and HCl. So we've got to remember that these are nucleophilic addition elimination reactions because the attacking group we're using is a nucleophile. So first an ammonia, and the second we used a primary amine. And also it's an addition elimination because we're adding this nucleophile and we're eliminating the chlorine and also a hydrogen.